All right, today we're going to cover logarithms, and logarithms are the inverse of exponential functions, and they help us solve equations like the one we see here. The answer to this equation is x equals 4, and that's because 3 to the 4 does equal 81, right? But we're like eyeballing to figure that out. I know that 3 to the first power is 1, 3 to the second power is 9, 3 cubed is 27, so then 3 to the fourth is 81. But what we're going to type into a calculator to figure this out, if we weren't to know it, would be we use a logarithm with the same base, log base 3, and then we're plugging in 81 as our input, and that's going to tell us 3 raised to the what power is 81, and x equals 4, so 3 to the fourth power is 81. And why this is helpful is in our current unit when we're covering compound interest and money gaining interest, if we don't know the time that it takes to reach a certain amount of money, right, then we can use a logarithm to solve for the time, right? If I'm getting 6% interest, how long until I hit 1500, right? So the log will help us solve for that. Will help us solve for that t, okay? Now, let's think about what logarithms are in our context or what they're telling us. So a logarithmic graph might look something like this, where it's getting flatter over time. And in our exponential graphs, let me go down here for a second. Our exponential graphs, our x-axis has been time. We're plugging in a certain amount of time, and then it's telling us how much money we have, right? So our y-axis is dollars. So now when we do a logarithm and it's an inverse, it's going to swap those. So now our x-axis is going to be dollars and our y-axis is going to be time, right? So then what this is basically covering is when we travel a horizontal distance, that's money we're gaining, and vertical distance is money we have now. So it could be that, let's say that this distance is $1,000 and that's how long it took, right? So this is one, and I'm drawing with my finger here, so sorry if this is messier than normal. Okay, $1,000. Okay, and basically what's going to happen is as we keep gaining $1,000, you can see that that time is getting smaller and smaller. I can't quite draw straight right now, but you get the idea. Because this graph is flattening out, as we gain $1,000, the time taken to gain $1,000 is shrinking, right? Because our interest is compounding and we're making more money, right? So an idea with logarithmic scale is that a linear distance is not always the same impact, right? So at first, when we want to gain $1,000, that may take a lot of time, but then over time, that $1,000 becomes less significant because we're gaining it faster and faster and faster, and that's the kind of thing we can analyze if we're able to work with logarithms and solve equations using logarithms. Okay, so one thing that you need to write down right now is our change of base formula. So we have, let's say for example, log base 2 of 13 equals x, okay? What we want to know is 2 raised to what power equals 13, okay? I don't know what that is, so I have to use a logarithm. And I also can't eyeball this because 2 to the first power is 2, 2 squared is 4, 2 cubed is 8, okay? And 2 to the fourth is 16. So my x value is going to be somewhere between 3 and 4, but it's going to be a decimal. I don't know exactly what it is. So I have to plug this into a calculator. And you can actually plug this into a calculator. There are ways to do that. You can plug it into Desmos just as it is, just exactly as it looks here. But if you have a less complex calculator, or if you just want another way to do it other than plugging in with the base of 2, you can actually use what we call the change of base formula. And this is what you need to write down. So in your calculator, if you just type the log button, that automatically does log base 10. So we can do log base 10 of 13 divided by log base 10 of 2, and that's going to be the same as if we took the log base 2 of 13. This is going to be important for later, and I believe that equals like 3.7 or something like that if you type that in. Okay, so then that gives us logs of decimal numbers, okay? Or logs where the answers are decimals. So let's try a couple logs really quick just to make sure we understand them, and I'm going to pull this directly from the lecture slides, so let's see. So if we say log base 5 of 125, you tell me what that is. Okay, log base 2 of 64. Log base 2 of 1 over 8. And then let's do one more. Let's do log base 3 of 15. And for this last one, you have to use the change of base formula. So you should go ahead and pause the video, and when you're ready to see the answers, you can unpause and I will start walking through them. Okay, so answers: 5 raised to the what power is 125, 5 raised to the what power is 125, 5 raised to the third power is 125. Okay, 2, I kind of just count out 2 every time just to make sure. So 2 to the first is 2, to the second is 4, to the third is 8, to the fourth is 16, to the fifth is 32, so 2 to the sixth is 64. And then when it's a fraction, that means that the exponent must be negative. So 2 to the third power equals 8. So 2 to the negative third power is 1 over 8. For this last one, we have to use the change of base formula. So we're going to say, we don't have to, but that's one way to solve it. Log of 15 divided by log of 3. Okay, I plug that in, and I'm getting 2.46 if we round. Okay, it's about equal to 2.46. Okay. So now we can actually use logs to solve problems. So let's say we have $4,000. It's gaining that 4.15% interest that Apple's currently offering. Okay, compounded monthly. So I want to know how long it's going to take for us to get $1,000. How long will it take for us to earn $1,000? So we have $4,000. Okay, we are gaining our 4.15% as a decimal divided by 12 raised to the 12t. Okay, and if we're gaining $1,000, what that means is we now have $5,000. Okay. So this is going to be our time taken to gain $1,000, and we need to solve. Our goal is to solve for the t value because that's our time. So we need to do algebra to isolate the t. So the first thing I need to do is divide the 4,000 over to the other side. Okay, so on what I have is on this other side I have 5,000 divided by 4,000, which is actually equal to 1.25. Okay, and that's equal to our base of 1 plus 0.0415 divided by 12, and then raised to the 12t. So I still need to isolate t, and now what I have is I have my exponential base by itself. Okay, so if I have an exponential base by itself, and I'm trying to solve for its exponent, now I can use my log. Okay, so I can say log base 1 plus 0.0415 divided by 12. That's my base. And then what we do when we set up these log equations is we're going to swap the other two pieces. So the exponent is attached to the base, and this is the answer. So now we're going to make it so that the answer 1.25 is attached to the base. So I'm going to put 1.25, and that's going to be equal to the exponent. They have swapped places, right? And this is nice because I'm getting closer and closer to isolating t. Okay, all I need to do here is divide by 12, right? But I also need to know what this is equal to, and that's where my change of base formula can come in. Okay, so I'm going to apply the change of base formula to this so I can figure out what it is, but then I also need to divide by 12 so that I can solve for t. Okay, so let's do that now. I'm going to pop over to another slide. So I have log on top of 1.25, and I'm going to divide by log of my base, which was the 1 plus 0.0415 divided by 12, right? And that was equal to 12t, so I need to divide this whole thing now by 12 so that I can get my final answer. All right, so when you type this in, you should do the top part first, and then you can hit enter and then divide by 12, or you can plug it all in at the same time as long as you're getting about t equals 5.4 years. Okay, that's what we should be getting. Okay, so another example would be if we have $10,000 and that's gaining 6% interest per year, okay, compounded yearly. How long does that take to reach $12,000? So again, we can say 10,000 times 1.06 raised to the t now because we're just compounding yearly, and that's equal to 12,000. Okay, what is t equal to? Again, we need to isolate that t. So our first step is to divide the 10,000 over to the other side. So I have 1.06 t equals 1.2. All right, and now I need to solve for my t. So again, I have my base here, which is attached to t, and I'm going to do log of that same base, log of 1.06, okay? And then the t was attached to the base. Now the 1.2 is going to be attached to the base, so we can solve for t. And now this is a simple change of base formula. If we don't want to plug it in as it is, this is going to be a little bit easier for most calculators. Okay, log of 1.2 divided by log of 1.06. And that is 3.13-ish, 3.13 years. So don't forget the context here. That means if you're gaining 6% interest on $10,000, it's going to take about 3 years for you to gain $2,000 for a total of $12,000. And that's what logarithms are telling us. Okay. The last type of example I want to show you is we did these examples where we were trying to compare two situations and see how long it takes for one to catch up to the other. So one person has $1,500 and they're gaining 5.5% interest per year, compounded yearly. Okay, the other person has more money, $2,000, but they're gaining 4.5% interest per year. Okay, and I want to know, this person one is going to catch person two at some point because they're gaining more interest, but we don't know how long exactly that's going to take, right? Because this person that currently has more money. So what we need to do is set up two functions and set them equal to each other. So if I say 1,500, right, times 1.055 raised to the t, I want to know how long it's going to take before that is equal to 2,000 times 1.045 raised to the t. Okay, how long is that going to take? Before we kind of guessed and checked on this until we got the two numbers to be equal, but there's a way we can do this algebraically now that we remember how to do logs. Okay, so what I want to do is I want to take the 1,500 and get it to the same side as 2,000 by dividing over, but I also want to get the bases on the same side. So now the initial values are on the right side. So I'm going to take the base and I'm going to take it over to the left side. So I have bases on one side and I have starting values on the other side. So I have 1.055 raised to the t divided by 1.045 raised to the t. And that's going to be equal to 2,000 over 1,500. And this is still challenging because what I want to do is isolate t, but there is currently a t there and a t there. So that makes this a lot harder algebraically, but this one actually isn't so bad because if this is raised to the t and this is raised to the t, we can rewrite this so that they're both raised to the t. And I'm just going to do it over here. So we have 1.055 over 1.045, and they're both raised to the t. Okay, both raised to the t. So now we have a base, right? And we have an exponent. And that's all that we have on the right side, so we should be able to use a logarithm now. It's going to get a little bit messy. Here we go. So we're going to use our log. And what's our base? Geez, I'm struggling already with my finger here. 1.055, 1.045. Again, this is a 5. That looks better. Okay. And then this is of, I had to jump over here. I ran out of space. This is of 2,000 over 1,500, and that's going to be equal to our t value. Okay. So now I can do that change of base, and I can do log of that 2,000 over 1,500, and I need to divide that by log of 1.055, 1.045. Okay. And that is going to give us our time taken for the catch-up. Okay, so we have log of 2,000 divided by log of 1,500. Or sorry, just log of 2,000 divided by 1,500, all in one. And then you should be doing log of 1.055 divided by 1.045. And I'm getting 30.21 years or 30.2 years. 30.2 years. And this is a general formula you can use now, just over here, because all those algebraic steps we just took, are repeatable just with different stuff plugged in. Okay, so you can, if you're doing a catch-up problem where you're trying to figure out, compare two examples and see how long it's going to take for one to catch up to the other, every single time you can do log of bigger starting amount over smaller, and these are just, this is dollars, right? Bigger starting amount of dollars over smaller starting amount of dollars, okay? And then divide that by log of bigger interest divided by smaller, okay? Okay, so there are lecture slides for today that kind of follow this lesson that you can review, and then there's a worksheet that you can work on to practice these concepts. If you're able to finish that worksheet and submit it on Google Classroom, then you can have a study hall for the rest of the period.